Okay, so thank you very much. So it's a pleasure for me to present part of my research. So I'm sorry because I think some of you have already seen most of it, in fact, in Carges or also at my last seminar I have done last year. And I'm going to talk about the possible influence of thermal weakening on the dynamics of rupture. And also, I wanted to say, if you have any questions, stop me during the presentation, and I will answer you if you want more details on some slides. So I'm mostly working at the scale of laboratory to understand earthquakes, and all the work I will show you today, in fact, has been mostly conducted by Federica, that is a PhD student I'm co-advising in Lausanne, so where I was before to arrive here. So I'm trying to reproduce earthquakes at the scale of laboratory. So what happened during earthquakes? You all know that, but I will start again to talk about it. So here you can see in background colors the Central Glass fault, and as you know, in fact, the load start to increase in the upper part of the crust because of a ductile deformation at depth where the rocks can deform plastically. And these continuous displacements that occur at depth increase the stress acting on the fault in the upper part, where the rocks deform first elastically. Up, you start to have the local rupture of part of the fault during the nucleation of instabilities. So, for instance, at that stage, and up to a critical size of the nucleation of the initial rupture length, there is a dynamic propagation of the fault. And this allowed to release the energy stored during the interseismic period. And the important thing is that there is two main important energy that correspond. The first one to the blue area, that is the radiated energy, which corresponds to the energy released into waves in the medium that are at the origin of the ground motion. And so this energy is well estimated by accelerograms and geodesy. In fact, it's there is energy that we can estimate in seismology, at least for large earthquakes, because for small earthquakes, we have some attenuation issues because of the high frequency content of the signals that are lost due to the attenuation of the medium. And the second energy that is really important, and it's the one I'm mostly focusing at understanding, is the fracture energy. So what is the fracture energy? The fracture energy, in fact, is the energy required to propagate the fault, so to unzip the fault, propagating the seismic rupture. And this energy is expected to be a function of the stress intensity factor that developed during the propagation of the cracks. And you all know, I think, that when you have a crack, at the tip of a crack, you develop the stress intensity factor that allow, in fact, to increase the stress and facilitate, let's say, the propagation of the seismic rupture. So the problem is that the fracture energy is not really well constrained by seismology, and is really important in terms of source physics. So I'm showing you here a quote that I found in the paper of Teng Fong Wang that was saying in 1982 that lacking detailed knowledge of the rupture process, the value of GC, the fracture energy, is the minimum amount of information required for any meaningful modeling of the source dynamics. So the first question I want to address is, what do we call fracture energy in seismology, in fracture mechanics, or in the field? So from what I know, in fact, the fracture energy was defined for mode 1 crack and is based a bit on Griffith's theory. And in such theory, the fracture energy corresponds really to the energy required to propagate a mode 1 crack in a quasi-static point of view. So there is no dissipative process at the crack tip, so there is no cohesive zone. And in this case, in fact, the fracture energy is really proportional to the specific surface energy that is a material properties. And this specific surface energy really mean that what is the energy required to propagate a given surface of a new cracks. And this fracture energy, based on that definition, is a bit similar in linear elastic fracture mechanics, where in fact you can see that the fracture energy defined in such framework is also a function of the surface energy for modern crack still, and is also a function of the stress intensity factor. So this is the definition in mode 1. So in this case, we can think that the surface energy and the fracture energy is scale dependent in the material properties. But in fact, we have seen in the past and in more recent results that is a bit more complicated because it also depends on the scale of observations. So here I'm showing you a scheme of a material that is going to fail with a rupture speed that is CF. And in fact, what we know is that the evolution of the cohesion during the propagation of these cracks is scale dependent in the sense that the cohesions at the crack tip, where we have distributed cracked and plastic flow along the crack tip, is different than where we lose a bit the cohesions and from the scale where that is completely cohesionless. And so if we plot the evolution of stress within this crack propagation, the fracture process zone is kind of effective. So the fracture process zone is really the size on which you lose the complete cohesions on the crack tip, along the crack, sorry. And the interesting thing is that the change in cohesion is also not purely linear with a distance to the crack tip. So it means that following where you are at the scale of observation, the fracture energy that is a function of this area can be scale dependent. So this is for mode 1 crack, but it's also true for mode 2 crack. So in mode 1, you have in pure tensile mode, but in mode 2, we can see the same things because the evolution of stress is expected to depend on the slip occurring behind the crack tip. So this is what I took from the paper of Teng Fong, but also from the paper of Ida and Palmer and Rice, where authors suggested that the fracture energy correspond more or less to the integral of the change in stress with accumulative slip behind the crack tip. And you can see also that this area is expected to depend on the stress intensity factor as it is in mode 1 and as I show you in the first part. So in the past, from laboratory experiments and also kinematic inversion in seismology, people try to estimate this fracture energy as a function of the integral of the slip and within the stress change occurring far from the crack tip. So why it's important to estimate earthquake fracture energy? So here I'm showing you the movie of the propagation of the seismic sequence of Parkfield that has been modeled by Sylvain Marbeau. And as you know, in fact, nucleation of big earthquakes, the propagation of big earthquakes is divided in different stages. So for instance, you will see here that before the nucleation of the big earthquakes, we have first small ruptures that propagate more or less close to the hypocenter of the big earthquakes. And you can see that when we start to propagate the rupture along this area, in fact, you have first a nucleation stage that corresponds to a slow extent of the rupture. And then when you reach a critical size, you have the dynamic rupture of the entire fault. Then after you have the slip occurring on the macroscopic rupture, and then after the fault remains stuck. So you are coming back to quasi-static loading. And this up to a second rupture event that occurs first on that side of the fault, and that will induce stress transfer to nucleate a second big rupture on the other side of the fault. So why it is interesting to understand fracture energy in this context is because, in fact, if we looked at the history of such earthquake sequences, so it's a bit different here. It's not the same earthquakes. It's a pure simulation that has been done by Mathias Levien. In fact, what you can see is that here I'm showing the rupture of an heterogeneous fault system. And you can see a first nucleation that occurs here with a crack propagations that arrest here. And then after you have stress transfer that induce nucleation on other part of the fault. Up, you have the rupture of the entire fault system. And what I wanted to show here is that if we know the fracture energy along the fault, let's say, we can estimate three different, what is that? Sorry. We can estimate the different stage of the rupture of the entire fault system. So the first thing we can estimate with the fracture energy is the nucleation length. For instance, the minimal nucleation length that can induce the dynamic propagation locally along the fault plane. The second thing that we can estimate, if we know the stress distribution and so the fracture energy along the fault, is the propagation, the rupture velocities of the rupture front propagating along the fault, which is a function of the relay wave speed, of the effective fracture energy, of the critical fracture energy, and of the energy release rate at the rupture tip. And the last parameter that we can estimate is the final rupture length, because we know by definition that rupture will propagate since if the energy release rate, which is really the energy released at the rupture tip, remains larger than the fracture energy allowing to propagate the rupture along the fault. So if this energy release rate is slower than the critical fracture energy, rupture will stop along the fault. So does it work in nature or at the laboratory scale? So here I'm showing you an experiment conducted by Sumaya Ato in 2013, where she highlighted that she was able to describe the nucleation of instability in PMS, so in a polymer. And here you can see that here is the time, and here is the distance along the fault. And you can see the development of steep instabilities that grow slowly and start to accelerate to its dynamic propagation. And what she observed is that if we increase the normal stress acting on the fault, we shrink, in fact, the nucleation length that corresponds to the critical length at which the rupture starts to propagate very fast. And the interesting point is that Yoshi Kaneko in 2016 was able, using retain state framework and also the definition of fracture energy, to model these experimental results. So it means that if we know the frictional properties of the material and, for instance, the fracture energy of the material, it's possible using retain state framework to model such behavior. So this point was for nucleation. The same exists in terms of propagation. So here is coming from experiments conducted by the group of Jay Feinberg in Israel, where they are able to monitor with a very accurate precision the rupture speed as a function of the rupture length. And as I showed you before, the propagation, the acceleration in the rupture velocity at a given point of the fault is expected to be a function of the equation of motion. And you can see that using LEFM, linear elastic fracture mechanics, they were able to show that knowing both the energy release rate along the fault plane during the rupture propagations and the fracture energy, they were able to predict the evolution in terms of rupture speed as a function of the distance to the nucleation point. So the final point that I wanted to address is the rupture arrest. Here I'm showing you same kind of experiments that has already also been done by the group of Jeff Finder and by Elsa Bayer in 2016, where authors were able to induce at the scale of the laboratory along the PMMA interface also finite rupture. So you can see here different events, successive events, and in blue, in fact, you can see the extension of the rupture during the successive events that occur along the interface. And using the same estimates of energy release rate and initial fracture energy along the interface, they were able to show that the length of rupture can be predicted by LEFM and by these equations. And here you can see the evolution of the measured length for each events that they were able to record during a lot of different experiments. And here you can see the value of the prediction using this equation. So is it always the case? And is linear elastic fracture mechanics always applicable to earthquake mechanics? So by definition, we can apply LEFM to earthquake mechanics if in fact the residual stress that corresponds to the minimal stress achieved far from the rupture tip become constant. And so if we are out of the cohesive zone. So what does it imply? This definition is that this implies that the fracture energy that corresponds to that area is expected to be constant at a given rupture size. And if it is the case, if LEFM apply, we expect a square root singular field for the peak in slip velocity close to the rupture tip, and also for the stress singular field at the rupture tip. So is it applicable to earthquake mechanics? Well, is not, probably not, because what we know from seismology is that the fracture energy derived from seismology, so with the hypothesis behind these estimates, there are a lot of hypotheses, so this scaling has to be taken, knowing that there is a lot of hypotheses behind. But what we know is that the estimates of the fracture energy from seismological data looks to scale, seems to be slip dependent. So the larger is the seismic slip, the larger is the values of apparent fracture energy. And so it's not a constant. And also what we have seen is that these values of fracture energy are much larger than what we can find in terms of material properties in rocks. So we see this kind of scaling? It's possible that it's related to the weakening that occur during earthquakes. So I wanted to show you that movie that I think you have all seen already. This movie is coming from high velocity experiments. What we do in such experiments is that we have two hollow cylinders of rocks, and we impose a given slip velocity function that is a seismic slip velocity during the experiments. And what we record is the displacement and the evolution of stress. And what we have seen is that during such experiments, we have the melting of the rocks because of the heat generated during the experiments. So here I'm showing you slow motions movies of such experiments. So you can see that once we reach a critical displacement, we start to have a melting of the fault surface that allows to reduce the stress along the fault. So using the measurement that we can have during these experiments, that looks like that. So here you can see the shear stress as a function of sleep. It's possible to integrate these curves to have an estimate of what I call here EG, that is a proxy of what we call fracture energy or a breakdown work in seismology. And the interesting observation is that using this kind of experiment that correspond here to the red curves, and the other symbols correspond to natural data coming from seismological estimates, you can see that in high velocity friction, when we are melting or thermal weakening along the fault, we also observe this slip dependency of the fracture energy. And so the larger is the slip during the seismic, the larger is the slip during the earthquakes, the larger is supposed to be the breakdown work. So it was a long introduction. So now I'm going to show you a bit what we have done on this topic with Federica the last year. And the answer I will try to address are the following. What are the parameters controlling the nucleation and the propagation of earthquakes? Is there a scale dependence in the fracture energy? And in which way thermal weakening that are expected to occur during seismic sleep can contribute to the dynamics of rupture? So what we have done with Federica is that we have these really simple experiments that is really similar to the one used by Jeff Feinberg in Israel, but also other people in the world. And what we do is that we have two blocks of PMMA on which we glue strain gauges at different locations along the fault. And we also have acoustic sensors to record the seismicity and stress sensors to monitor the stress change during stick slip events occurring along these experiments. And so we use these strain gauges to have a direct estimate of the fracture energy during our experiments. So these strain gauges are very small because we need strain gauges that are smaller than the cohesive zone along the fault. And this allows us to measure the full strain tensor during the experiments. So why do we use PMA? Is because it's a continuum medium. It's made of amorphous polymer. And the cohesive zone is really small compared to the length of the experimental fault, that is, in this case, 20 centimeters. So here I'm showing you a detail of one experiment that we have conducted. So first, we increase the normal stress acting on the fault. We increase the stress manually up to reach a given values. And then we start to increase the shear stress also manually by increasing the stress on a pump that allow to increase the stress in the slip directions. And once we reach a critical stress state along the fault, we induce stick slip events. And these events induce a stress drop along the fault that is also related, linked to the propagation of waves that we are able to record using accelerometers located at different positions along the fault plane. And what we observe is that the larger is the stress acting on the fault, the larger is the stress drop during the event. And so if we increase again the stress after each event, we are able to induce different stick slip. So we are able to mimic kind of earthquake cycle at the scale of a very small experiments in PMMA. So now I'm showing you the detailed results of one single event. So it's this first event that occur along the interface. And here in black lines, you can see the evolution of the strain recorded at different locations along the fault. So at this time scales, it looks that we have a stress drop that occurs at the same time that are associated to the accelerations of particles recorded by the accelerograms, by the blue curves. So if I zoom really on that events that correspond really to the propagation of the rupture of the interface, what you can see is that the strain gauges are allowing us to estimate the rupture speed during each event. So how we do that? So you can see that each lines correspond to the measurement of the strain during at different locations along the fault. And if we take the increase of stress as a proxy for the rupture tip arrival, we are able, knowing the position of the fault and the time difference, to have an estimate of the rupture speed during the propagation of the rupture. So why do we need this estimate of the rupture speed? Is because what we are also able to record during the dynamic events is the stress intensity factor that propagates at the rupture tip. So here I'm showing you a picture of a quasi-static crack propagating, and using birefringence of the material and polarized light, you can see, in fact, the development of the stress intensity at the rupture tip. And what we are able to measure during the experiments is with strain gauges is really the development of such and the propagation of such stress instability. So if I plot it at the stress intensity factor, the strength singularity at the rupture tip during one event, I can plot it as a function of a distance from the crack tip if I consider a constant rupture speed during each event. And knowing that experimental data, it's possible to model them, knowing the position of the strain gauges along the interface and knowing the rupture speed. And the important thing is that this allows us, using different frameworks, to have a direct estimate of the fracture energy. So here you can see a comparison between the experimental curves that correspond to the black, the red, and the blue curves that correspond to the strain to the strength intensity at the rupture tip in 3 different directions, and the black and the gray dashed line correspond to the result of a modeling. And this modeling, the only unknown, correspond to the fracture energy. And considering that the fracture energy is equal to the energy result, we have a direct estimate of the fracture energy. So once we have this estimate of the fracture energy that controls the dynamics of the rupture tip, that really control the strain singularity, we can compare it with the integral of the evolution of stress as a function of sleep. And if you remind what I told you before, this is a second way to estimate the fracture energy, looking at the evolution of stress as a function of sleep occurring far from the rupture tip. So this is what we have done. And the interesting thing is that, as you can see, the release of stress is divided in 2 different stages. First, within the first microns of sleep, we have a strong stress release that occurs within a critical sleep distance that we can estimate from that equation, knowing the fracture energy that controls the dynamics of the crack tip. So if we compare the integral of curves up to this critical sleep distance that we call the near tip breakdown work, what we have seen is that the near tip breakdown work, so the blue integral, corresponds to the value of the fracture energy that we estimated at the rupture tip using the strain intensity factor. So that corresponds to the energy release rate at the rupture tip. While in fact, you can see that there is a second large-scale weakening that occur far from the crack tip that correspond to the complete breakdown work. And these values of breakdown work are much larger than the energy release rate that are measured at the crack tip. So what does it mean concretely? Is that at the scale of our experiments, only a part of the complete breakdown work, only a part of the total weakening control the dynamics of the rupture tip. And only for a few events, it looks that the energy release rate at the rupture tip is larger than the near tip breakdown work. So only for few events, maybe part of the dynamics of the crack is controlled by the long tail weakening. But anyway, each event, each energy release rate remains much smaller than the complete breakdown work. So it means that we don't see any case in base experiments where the complete breakdown work controls the entire dynamics at the rupture tip. So why the energy release rate is mostly controlled by the first weakening? This is a question I want to try to address now. So it's because, in fact, during our experiments, at the scale of our rupture experiments, the initiation, so the nucleation and the initial propagation of the rupture is mostly controlled by the first weakening stage that occurred within the first micron of slip. And in fact, if the initial stress along the fault, the background stress is relatively high, so if the initial energy in the medium is high enough, the accelerations of the rupture front as a distance from the nucleation is very strong. And because of that, the information of the second weakening stage that occur after these strong accelerations doesn't have a time within our rupture time to catch up the first rupture front that propagates initially because of the first weakening stage. So in which conditions we can see this large-scale weakening catch up the rupture tip and control the full dynamics? Well, it is when, if in case, for instance, if we had a smaller background stress, then in fact, if we have a smaller stress along the fault, the initial accelerations will be slower, and so the information of the second weakening are expected to catch up the first rupture tip. And in this case, in fact, we expect that the rupture can be controlled by the complete breakdown work, let's say. So this is what we have done numerically. So I think I'm a bit late, so I will pass on that part. If you're interested, I can talk to you about that later. But these really simple schemes that I show you, it's something that we demonstrated for numerical simulations. And it's something I have shown also in the last seminar last year here. So I'm passing on this slide and I'm going to talk about experimental case where LEFM is not applicable anymore. So what I'm showing you here is different experiments, and it's again the evolution of stress as a function of sleep during different stick sleep experiments. And what you can see is that the larger is the rupture speed, the larger is the change in stress and the weakening that occur with sleep after the rupture tip. And the interesting thing is that if you plot the integral of these curves, so the breakdown work as a function of sleep, you can see that we have a first strong increase in breakdown work with sleep. And then after, there is a second increase that is related to something different than linear elastic fracture mechanics. So as I have told you before, if we assume pure linear elastic fracture mechanics, we expect such evolution of breakdown work with cumulative sleep. And as I told you in the introduction, if LEFM was always applicable, we should reach a constant value for a given final sleep, because if you are out of the cohesive zone, you expect that the fracture energy cannot increase anymore with sleep, and you reach a maximum value that is expected to control the full dynamics of the rupture tip. And as you can see, is not the case. So the LEFM prediction is not working for each experiment. And in some cases, particularly true for the events that propagate at the faster rupture speed, we have a secondary increase of breakdown work with cumulative sleep. So what we have done is that we tried to do the same analysis to the same analysis of the sleep occurring behind the crack tip using a linear elastic fracture mechanics. So here you can see the evolution of breakdown work with sleep for one single event, and here you can see the evolution of sleep as a function of the position of the crack tip from the experimental point of view. And here is the evolution of the shear strain as a function of the distance from the crack tip also. So if we use the same framework that I have shown you before, that is linear elastic fracture mechanics, we can do the same analysis that we have done before, and we can try to obtain the best fit using LEFM. And if we do that, what we saw is that it's possible to fit more or less well the strain singularity, the strain perturbation of the crack tip, but we have a strong mismatch in terms of displacement behind the crack tip. And the important thing also is that the best solution for the fracture energy that we get for the best fit is much larger than the final value of breakdown work that we measure experimentally. That is here about 12 joules per square meter, where you can see that the best solutions have put values that is twice larger. So what we have done is that we try to analyze these experiments, these experimental data using unconventional theory. So what we can do is that we can see, as I told you, that after a critical point, we have a continuous increase of breakdown work with sleep. And from the slope of these curves, we can define an exponent that we called Xi. So sorry, it's not written here, but this parameter we call it Xi, and is allowing us to modify linear elastic fracture mechanics to have a second estimate of the strain field and of the displacement field at the rupture tip in a different framework. And so using elastodynamics equations, we solved the expected stress field as a function of the positions of the distance from the rupture tip and the position around the tip for such unconventional singular field. And so using such estimates of the Xi exponent, you can see that we can define the stress field. And if we do the same analysis, so in this case, the unconventional theory allows us to model the displacement as a function of a position to the crack tip using the Xi exponent and using the final value of breakdown work that we measured experimentally. And so what you can see is that using such new framework, we have a much better constraint of the experimental data, the red curves compared to the orange one. And it's also true for the strain singularity, mostly behind the crack tip, where we see the influence of the far field stress the far field stress. So why we have the development of such unconventional singularity order is because, in fact, in these experiments, the stress never reach a steady state value. And so, as you can see here, I'm showing you the evolution of the shear stress as a function of the slip rate that correspond really to that event. And as I just told you, you can see in that case that the shear stress, even far from the crack tip, never reach a constant residual value. So how do we explain this kind of stress evolution? Is probably related to a flash heating phenomena. So what is flash heating phenomena? Probably you all know, but it's related to the melting of asperities along the interface during rupture propagations. And so what we know is that at the scale of experiments, we are able to model the the rise of temperatures that is expected to occur at a given asperities during rupture experiments. And what we can see is that for such values of slip rates that we know that are accrued during our experiments, we expect an increase in temperature that is larger than the melting temperature of the Pma. So we know that at the scale of experiments, flash heating can occur in these experiments. It's not the case in all experiments, but in some events, it's the case. And also, people have shown in the past, so the group of Ares-Rozakis in Caltech, that they have the same kind of experimental data. So the black lines here correspond to the evolution of the shear stress of the friction, as a function of the slip rate. So it's the same kind of scale that we have in the experiments of Federica. And you can see that using flash heating theory, coupled with rate and state framework, they are able to model such kind of stress evolution. So finally, to try to compare all the different experiments that we have done, I show you here the normalized evolution of the breakdown work by the fracture energy that correspond to the one we defined from LEFM as a function of a normalized displacement, the displacement normalized by the critical displacement. And the black dashed line here corresponds to what we expect from linearistic fracture mechanics. So we see that in events that correspond to the slower rupture propagations, so between 0.2 and 0.4, let's say, times the Rayleigh wave speed, LEFM looks to explain more or less well the experimental data. But for events that propagate faster, in fact, you can see that we have this constant increase of the breakdown work with cumulative slip with an exponent of 0.6. And the black lines here correspond to two asymptotic solutions that we derived from flash heating theory that allow us to show that the first increase of breakdown work can be explained by flash heating in adiabatic regime. So if you neglect diffusion of the asperities, because these propagation time are very small compared to diffusion processes. And the second and unexpected increase of breakdown work with cumulative slip is explained also by flash heating theory with different parameters. So if you're interested, I can give you the details after the seminar. And you can see that we match very well the evolution of the breakdown work with flash heating phenomena. And this is because of this flash heating occurring along the interface that we develop unconventional singularity order that cannot be really well defined by linearistic fracture mechanics. So here are the conclusion and the take-home message. So the fracture energy controlling the rupture dynamics is, as I show you, scale dependent, even at the scale of experiments. So at small scale yielding, fracture energy looks to be a constant material that controls the nucleation and the initial propagation of the seismic rupture. But at larger scale, the fracture energy becomes a slip-dependent parameters and is expected to control partially or totally the energy release rate and the dynamics of the rupture if you have rupture lengths that allow for the far field weakening to catch up the initial rupture tip that propagates along the fault. And so finally, when the residual stress is controlled by diffusive processes, so it's never reaching a constant value far from the rupture tip, singularity order becomes unconventional, and this modified the equation of motion during rupture propagation. And in this framework, in fact, LEFM cannot be used simply to analyze the dynamics of the rupture front. So to finish, I will show you what is next and what I plan to do in GeoAzure within the next years, thanks to the ERC project that we got. So up to now, as I have shown you in this talk, is that we mostly analyze earthquakes at the scale of experiments along very homogeneous interfaces. And this allow us to analyze and to study regular release of energy, regular simple earthquakes that are expected to occur within the same form during the entire seismic cycle. And the advantage is that in the laboratory, we control most of the conditions, so we can have the details of the physics of rupture. So I show you also that in this kind of simple fault, we are able to predict the evolution of the rupture velocity and to predict the size of the rupture that propagates during the stick slip events. So the goal of the ERC proposal is really to study the same physical details of rupture, but along interfaces that present heterogeneities. And these heterogeneities are expected to explain why in nature the release of the energy within the seismic cycle is not only controlled by simple events, but is induced by many different kinds of events, such as very low frequency earthquakes, slow slip events, but also creep and stable slip along the interfaces. So how we will do it is that within this project, we will use still amorphous polymer as a proxy for rocks. And so we will be able to print seismic asperities within a seismic bulk to see the influence of heterogeneities during the propagation of events during our experiments that model the seismic cycle. So the first part of the proposal will consist in a deterministic predictability of the dynamics of the rupture. So we will try to understand the physics of rupture phenomena occurring along such heterogeneous interfaces. And in a second stage, we will try to study the statistics of the seismic events propagating in such experimental devices, and we will use statistics and deep learning. The second thing that we will try to do is that we will build a larger scale experiments, and we will try to develop at the scale of a laboratory geodesy. So coupling measurements of displacement located at different distance from the fault plane with digital image correlations of the deformation of the surfaces. We hope to be able to predict and to estimate the fault coupling and the fault slip during the seismic cycles. And this will allow us to test and calibrate geodetical inversions that are done in the field, because in that experiment, we will know the exact frictional properties of the interface, while in fact in nature, we don't know, we don't have strong constraint on the fault geometry as well as on the frictional properties. Finally, the idea is with these estimates of the fault coupling during the seismic cycle, coupled with the locations of the seismicity that we are able to locate using the acoustic sensors, we try to test the predictability in time and space of the seismicity. So here is a scheme of the apparatus that we will try to develop in the laboratory. So with Julien Hand, but also with Alexandre Chimanda and other people in the laboratory. So the idea is really to try to reproduce large-scale rupture at the scale of the laboratory to try to understand and predict earthquake motions. So the question we want to try to address is better constrain the seismic hazard at the scale of the laboratory, and to try to answer the following question: what do we need to predict earthquakes at the scale of the laboratory? And this to understand which kind of sensors we need to understand and measure the physics of earthquake phenomena. So thank you for your attention. It was really long. I'm sorry about that.